Alright folks, welcome back. We're continuing to talk about our second family of descriptive statistics, measures of variability. And if you remember last time, we closed things off by introducing the formula for one of those common measures of variability called the variance. We talked about how it sidestepped that problem that deviations have, where, again, adding all the deviations up always equals 0. So, before we get into how to calculate the variance and start looking at some actual data sets, a little bit of an introduction. This is going to be the first time, but not the last time in this class, that we're going to see two different formulas for the same statistic. We're going to see what are called definitional formulas and what are called computational formulas. Here's what the difference is between them. Here's how the role they're going to play in the course. So they're both different ways of getting the same answer. They're both going to give you the same number. So if they're used correctly, they're going to get you to the same place. That's the first thing to keep in mind. The definitional formula is closer to the mathematical logic that underlies the formula, sort of the why we calculate things the way that we do. So it mirrors that logic more closely. It also usually takes longer to do and it's easier to make mistakes with it. So definitional formulas, they help you keep track of what the conceptual big picture is, but they take longer, they usually have more steps, and it's easier to make mistakes. Computational formulas, they are designed to be quick. They're more efficient, they're less error prone, they get to the point more directly, they involve fewer calculations to get the right answer. But they don't mirror the underlying ideas as closely as the definitional formula. So here's the long story short. Which one to use? It's up to you. We generally in this class are going to talk about computational formulas almost exclusively, but if you can get to the right answer, I do not care how you get there. On your quizzes and exams, you are going to be given formula sheets that have both versions of the formula. It's up to you which one you apply. So all I care about is getting the right answer. I recommend that computational formula. You're going to have a better shot at getting there. But if you want to use the definitional formula, it's certainly not going to be something that's penalized. So we'll practice both at first, as I mentioned, and then we're going to switch entirely to computational formulas. Okay, so back to where we left things off last time, talking about the definitional formula for the variance. Again, we start by calculating those deviations, subtracting the mean from each score. Then we sidestep the deviation problem where they all add up to 0 by squaring them. Now the negative deviations become positive. By the way, because of this step here, a variance can never, ever, ever, ever be a negative number. Because we squared all those deviations, they're now all positive numbers or perhaps 0. So variance can only be 0 if every single score in the data set is the same. Otherwise, it has to be positive. It can never be negative. If you calculate the variance and you get a negative number, you goofed. Go back, review it. You have a guaranteed wrong answer. And some common mistakes in calculating the variance lead to those negative scores. So back to the formula. We've taken the deviation scores. We've squared each one of them. Then we just add them all up. This stage of the process is called the sum of squares. And again, we see the formula there that represents the first three steps together. Then we just divide it by the number of scores that we have, the number of squared deviations. And again, we call that the sample variance. So here's that compact version of the same thing, the sum of squares calculated in the first three steps, divided by the number of scores. So let's see what calculating variance looks like for those two data sets we introduced last time. We asked two groups of people how many friends they have. We're going to start with the first group of people who all report they have 3 friends. By the way, from time to time when we review data sets here, I'm going to organize things in different ways with here 4 different columns. I'm going to calculate each step one by one. Here's the thing, you don't have to calculate these things the way that I do, but you should have a specific organized strategy. This is a class where you're going to be asked to calculate things like the variance, and unforced errors are killers there. You really, really want to minimize those. So have a clear, consistent way of organizing your operations so that it's very obvious how you'll proceed through it and you don't lose track of the calculations that you make. So long story short, here the first column represents our x, and in that case that's the number of friends. Here at the bottom we sigma them up, which means we add them up, and we add them up to 30. We calculate the mean by dividing that sigma x by the number of scores, which is 10, and the mean is 3. So the average score is 3. Deviation score is very, very boring. Notice there's no variance here at all. So everybody has a deviation score of 0. 0 squared is still 0. That adds to 0. our variance is 0. Not the most exciting calculation. Well, let's see what happens when we do have some variability in that same data set. So here, 5 people report that they have 5 close friends. The other 5 report that they have 1 close friend. So again, notice our sigma x is the same. It's still 30. Our mean is still the same. It's still 3. The mean doesn't tell those distributions apart. But now we have deviations. And notice we have it organized, so we just subtract across. 1 minus 3, negative 2. 5 minus 3 is 2. If we added all these up, they'd add to 0, so we're not going to do that. We're going to square them. They all square to 4. When we add up all of these 4s, and by the way, what's happening down here, that's our sum of squares. When we add up all these 4s, they add up to 40. So we take that sum of squares of 40, we divide it by the number of scores, which is 10. Our variance is 4. Now we have a descriptive statistic that lets us tell those two distributions apart. They have the same mean, but the difference in spread that they have isn't being reflected in the mean. The variance now lets us quantify that dimension. So that's the definitional formula. It's closer to the logic of what we're doing, sidestepping that deviation problem, but it's a few more steps and it's a little slower. Here's the computational formula. The first thing that we do is we're going to add up all the scores in the data set. That is sigma x. So we add up all the scores in the data set. After we add them all up, we're going to square this number. Then we're going to divide it by the number of scores. We then subtract that result from the sum of each score squared individually. That sounds a little intimidating, but it just means you're taking every score, you're squaring it, then you're adding up all those squared scores. Then we divide the total by the number of scores again. So steps 1 through 3 again give us our sum of squares, then we divide by the number of scores. Here's what that formula looks like. And here's the thing, this looks more complicated than the definitional formula. Trust me, as you'll see when we calculate it, it's not more complicated. Here are the main things to keep straight. We have a sigma x in parentheses squared. That means do what's in the parentheses first, add up all the x's, that's step 1, then square that number, that's step 2. Over here we have the same symbols but with no parentheses. Here our rule is the exponent happens first. We square each score individually, then we add them all up together. A very, 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 very common mistake is for people to either reverse how they're supposed to calculate these or calculate both of them the same way. Those parentheses are crucial. Make sure you're accounting for them. When sigma x is in the parentheses, we add up all the x's first, then square them. When sigma x is not in parentheses, we square all of the x's, the scores first, then we add them up. So again, after we divide sigma x squared by n, that's steps 1 and 2 over here on the right side of the denominator, or the numerator. We subtract it from sigma x squared on the left, and we divide that by our n. So let's see what that looks like with our same data sets. Again, our boring data set. Notice, by the way, how many fewer columns they have. I have just 2 columns, and then I add up what's at the bottom of them, and then I'll have all the information I need. So again, our x, everybody has a score of 3. That adds up to sigma x of 30. When we square them, they all square to 9. Sigma x squared is 90. And the only other piece of information we need is the number of scores, which is 10. That's it. Notice how much quicker this is. All I'm doing is adding up all the scores I already have, squaring them individually, and adding up those squared individual scores. And the only other piece of information I need is my n. So here's what that looks like in our variance formula, our computational formula. Sigma x squared, all the scores squared and then added up, goes here on the left side of the denominator, or the numerator, excuse me. Sigma x, all the scores added up, is going to be squared over here on the right side of the numerator, and then that's going to be divided by the number of scores. And here again, 30 squared is 900, divided by 10 is 90. 90 minus 90 is 0. We have no variance present here. Here's our slightly more interesting data set where we have some variability. And again, sigma x is the same. The mean would be the same, though notice we don't have to calculate the mean to get it this way. We square each score individually. 1 squares to 1, 5 squares to 25. We have a different sigma x squared of 130. The number of scores remains 10. We plug these numbers in, and what we see is, again, sigma x squared, the score is all squared and then added up is 130. Sigma x 30, that squares to 900, divided by 10 is 90. 130 minus 90, our sum of squares, our numerator is 40. We divide that by 10, our variance is 4. Now, if that all went by kind of as a blur, I recommend trying to calculate this stuff from scratch. going into the practice problems, going into the book, going into the homework. Get a little bit of experience calculating this stuff by hand. Make sure that you're able to get to the correct answers. So again, the mean was the same for both of our groups, but the variance, no matter which way we calculated it, was 0 for our first group because there were no difference in the scores, and 4 in our second group. The mean does not let us tell those distributions apart. The variance does. That's the end. We are going to continue from here to talk a little bit about calculating and using another measure of variability, what's called the standard deviation.